In the last video, we found parametric equations for a curve called a cycloid. This is the curve that you get if you have a circle, or a wheel, let's just say, that is rolling along the ground, and you look at a point on the edge of that wheel, and you look at the path that that point traces out. This path is called a cycloid, and it looks like this series of arches that go on forever and ever. We found that the equations for a cycloid made by a circle of radius 1 are x equals t minus sine t and y equals 1 minus cosine t. Now, of course, if you want to change the radius of the wheel, you could always multiply both your x and y equations by some new value, some new radius, and that will actually expand the cycloid in both the x and y directions by a factor of whatever the radius of the wheel is. But let's just stick with radius 1 to be simple. What I'd like to do now is use calculus to help us figure out some questions about this curve. The first question is this. I'm not sure that I've drawn this curve accurately. I just sketched it. And I sketched it with a corner, a cusp, at this point right here at the origin, and a cusp over here when x is 2 pi, that's also when t is 2 pi, and so on. I made a sharp corner there. Is that really accurate? I haven't watched the actual wheel rolling along and the point on the edge of the wheel and the path it's taking. I don't know for sure if I've drawn this correctly. Let's see if we can get some more information. In particular, I'm not sure if that should be a cusp or the following. Maybe that point should look like a cusp, like I drew, a sharp corner. Or maybe it should look like this. Maybe we should have a sort of a smooth curve here that carries on like this. That doesn't actually make a sharp corner. Or maybe it should actually move backwards just a tiny little bit, make a little bit of a loop. Like that. If we zoom in really, really close on that point, which of these three curves does it actually look like? Well, what distinguishes these? In all three cases, the point that we're looking at is the lowest point in the y direction. It has to be because it's the point where the nail on the edge of the wheel is at the bottom of the wheel. The lowest point it can be. It can't possibly go lower than 0. This is the lowest point in the y direction. It's a local minimum. And then what that tells us is that the derivative in the y direction, dy dt, should be equal to 0. That means that our y starts off decreasing, decreasing, decreasing down to 0, and then begins to increase again afterwards. We have a local minimum. So dy dt must equal 0 at that point. In all three cases, dy dt must equal 0 at that point. But what is dx dt? Well, in this middle case here, our x is moving along, going to the right always. And it continues going to the right at this point. So if it's the middle case, we call these case A, case B, and case C. If it's the middle case where you just have a smooth portion of the curve there, then dx dt should be positive at that point, because the x is continuing to increase at that point. On the other hand, what if it's the third case, case C? What if we end up with a little bit of a loop there where this point briefly goes backwards? We'll be moving along, x is increasing, x is still increasing. Oh, all of a sudden, x starts to decrease and goes backwards and then begins to increase again and increase again. So if it's the third case, then at that point, dx dt is negative. What will be the case at a cusp? Well, to have a cusp, you have to have a point where dy dx, the slope of the tangent line, is actually undefined. And in order for that to happen, we need dy dt to equal 0, and we also need dx dt to equal 0. In other words, we need that point to completely stop moving for just a moment. It can't be still moving forward as its vertical motion pauses, and it can't be moving backwards temporarily as its vertical motion pauses. It needs to completely stop if it's the first case. So which case is true? So let's try and figure this out. We know that our curve is defined by the following equations. We know that x equals t minus sine t, and y equals 1 minus cosine t. So our question is, what is dx dt and dy dt when t equals 0, or 2 pi, or 4 pi, etc. These are all the points that we think might be cusps, but we can't be certain yet. Now, dy dt had better be equal to 0, because we believe we have a local minimum at that point, a local minimum for the y. So if we don't get a 0 for dy dt, then we actually have a totally wrong equation. Dx dt, we really don't know yet. We'll have to figure it out. So let's figure this out. Let's work it out. So let's just verify, first of all, let's make sure that dy dt actually reaches 0 at these places. So y is equal to 1 minus cosine t. What is dy dt? The derivative of y with respect to t. Well, the derivative of 1 is just 0, so I'll leave that out, minus the derivative of cosine t. But the derivative of cosine t is negative sine t, so negative sine t. So that means this is actually just positive sine t. What is dy dt at t equals 0? Well, then dy dt is going to equal the sine of 0, which is in fact 0. So we're good. Dy dt is definitely equal to 0 when t equals 0. This is also true when t is 2 pi or 4 pi or anything, because sine of a multiple of pi is always 0. So at all of those places that we believe are local minima, dy dt is equal to 0. Now we can check and make sure that it's a local minimum by checking the second derivative if we want to. I probably won't bother with that because it's pretty clear from the function that is the case. So a really important question here is, what is dx dt when t equals 0? That's what's going to answer the question, which of those three cases do we have for that local minimum? Do we have a cusp? Do we have is just sort of a smooth, rounded local min? Or do we actually have a loop where the particle temporarily goes just backwards for a little bit? So let's find that out. Well, our x is equal to t minus sine t. So dx dt is the derivative of this. That is going to be 1 minus cosine t. And at t equals 0, our dx dt, we'll just plug 0 into that, and we're going to get 1 minus cosine of 0. But cosine of 0 is 1, so we have 1 minus 1, which is 0. So that tells us that dx dt is equal to 0 at the moment when t equals 0. Let's go back and look at our three curves, our three possibilities. So we thought in the first possibility we have a cusp. That could only occur if dy dt equals 0 and also dx dt equals 0. In the other two possibilities, dx dt would have to be non-zero, so that the particle is actually in motion when we reach that local minimum. The only possibility that actually works, since we've found out that dx dt is equal to 0, is it must be this first possibility here, this first explanation that we have a cusp. So we do actually have a cusp, a corner, a sharp point in our graph. Going back to our original graph, it looks like this is pretty accurate. We do actually have a cusp here where we drew a cusp. Now, we could also ask a further question. What does the tangent line actually look like here? Technically, there shouldn't be a tangent line at a cusp, but you can ask what the derivative is approaching as we approach this point from the left or from the right. And we could ask ourselves, what is actually the slope of the tangent line approaching there? We could say, let's find dy dx and take the limit as t approaches 0. In fact, let's do that. So we found out that dy dt is equal to sine t. And we found out that dx dt is equal to 1 minus cosine t. Now what I'd like to do is find out what dy dx is. This is actually the slope of the tangent line. Well, it'll tell us the slope of the tangent line if we plug in a value for t. To get dy dx, it's very simple. We just take dy dt and divide by dx dt. So this is going to be sine t divided by 1 minus cosine t. Now, at t equals 0, what do we get? Well, dy dx, the slope of the tangent line, that should be sine of 0 over 1 minus cosine of 0. But the sine of 0 is 0. Now that's fine. But 1 minus cosine 0, cosine 0 is 1. 1 minus 1 is 0. So we have 0 over 0. That's not good. Don't assume that that's 1 or anything like that. We don't know what 0 over 0 is. 0 over 0 is undefined. What does this tell us? This tells us that the tangent line, and therefore the derivative, does not exist at t equals 0. Which we already knew, actually, because the point of a cusp is their function is not differentiable at that point. There is no tangent line. If there were a tangent line, the function would be differentiable. You wouldn't have a cusp there. So there is no tangent line at t equals 0 because there's no line that you can draw that just perfectly brushes up against the curve. But what can we do? Let's find the limit as t approaches 0 of dy dx. I'd like to know what the slope of the tangent line is approaching as we approach that point, from either the left or the right. In other words, I'll just draw a quick copy of this graph here. Now I know that I'm going to have a cusp at this point at the origin here and bounce off it. I can't actually draw a tangent line at this point that is the cusp here because there's no line that's tangent to that. What I can do is look at points close to this point and look at the slope of those tangent lines. And what I'd like to know is, are those tangent lines approaching a vertical line, or are they approaching something else? Is it different on each side? That's what I'd like to know. So let's work this out. Let's find the limit as t approaches 0 of dy dx. Dy dx we determined is sine of t over 1 minus cosine t. Now, if you try and plug 0 in right now, we already figured out what you'd get. You'd get 0 over 0. What tool of limits can we use if we have 0 over 0 appearing in a limit? We can use L'Hopital's rule. Now, at any time that you use L'Hopital's rule, you need to justify that use by showing that you first get 0 over 0 or infinity over infinity if you try and compute the limit normally. So we've gotten 0 over 0. That tells us that we are justified to use L'Hopital's rule. And that tells us we should take the limit as t approaches 0 of the derivative of the top divided by the derivative of the bottom. The derivative of sine t is cosine t. And the derivative of the bottom, the derivative of 1 minus cosine t, is going to be positive sine t. Now if we try and plug 0 in, we're going to get cosine of 0 over sine of 0. Now cosine of 0 is 1. Sine of 0 is 0. This is still undefined, but of course, when we're taking a limit, the rules are a little bit different, right? This is not an answer, but what this tells us is that the answer is either infinity or minus infinity. And which one of those hardly matters in this case, because what it tells us is that our tangent line, as we approach this cusp, is actually going perfectly vertical. So what that tells us is we don't have a cusp that looks like this. We have a cusp that looks very sharp, where the tangent line is 0. So it's not a sort of shallow cusp that has some defined angle. It's a very sharp cusp, where the tangent line actually goes almost approaches a vertical line as you get closer and closer to that cusp. So by using the derivatives of this function, the derivatives of x and y with respect to the variable t, and using the derivative of y with respect to x, which tells us the slope of the tangent line, we're able to get a lot of information about the shape of this curve. We figured out that we have a cusp, well, lots of cusps, infinite many of them, on this curve, and that those cusps are extremely sharp because the tangent line appears to go vertical as you approach that cusp.